Great, so this is an example involving what we call Bernoulli equations. So a Bernoulli equation, at least in differential equations, not to be confused with Bernoulli equations in physics, is something that looks of this form, where you have the derivative of y with respect to t plus y is equal to qt here with this extra y term. So what is this? So it's basically a first order linear equation, but then you have this y to some power stuck on here. And so it's kind of an almost linear as we look here, where everything is working out, but then you have this extra term. So some examples where this might, you might see this, you might see something that looks like, oh, it could be as simple as, something like that. It could be positive or negative. The only reason they have these restrictions on alpha is that if alpha is 0 or 1, it turns out to be a linear equation anyway. So say it was something like this. Now, you also could run across it, and it's also pretty common to see something that looks something like, say, you know, maybe have, I think when I see this, I more often see dy dt. Say we have a 1 over y squared, right, plus 1 over y is equal to 7, something like this, where this is actually equivalent in form to a Bernoulli equation, where you can sort of see if you had multiplied everything by y squared, it would look, very close to what's up there. In fact, if I wanted to be exactly what's up there, it would have been clever to put a 5 right here. So these are, in fact, equivalent. And the reason why you might prefer one or the other is, well, the top one is easier to recognize. The bottom one is actually more useful for our particular problems. So how you solve these? Here's what you do. You're going to use a change of variables. It's a clever change of variables that turns it into a linear equation. And so if I write it in the second form, my v is just this right here. So v is that term right there every time. Right? So there is stuff over here be like, oh, let v be y to the 1 minus alpha. No, I'm not going to do that. So v would be, I guess I shouldn't say that term, but v is the 1 over y in this case. So let's do this one. So in this case, if I call v 1 over y and substitute that in here, notice that dv dt will end up being the negative 1 over y squared dy dt. Right, if I take a derivative of 1 over y. But this matches. The only difference is we have this negative. And so to get this part here to match there, I'm going to multiply both sides by negative 1 here. So this gives me this yellow equation can now be rewritten as, I'll again do it in yellow, negative dv dt plus 3v is equal to 5. And now this is a linear problem, and we could solve that pretty straightforwardly. Let's solve it. I would just first deal with that negative. So dv dt minus 3v is equal to negative 5. And we've seen this one a good amount to say that my v would then have to be, let's see, the homogeneous solution, right? So some constant times e to the positive 3t, and then plus my particular solution of, let's say, 5/3. So there's my v. In order to find out what y is, recall that this was given as 1 over y. So let's just flip everything upside down. So y then is equal to 1 over all that junk. Great. I feel like I'm a little gung-ho at the moment. So that's a Bernoulli equation. That's how they work. Let's do one more while we're at it, just to hopefully make it make a good amount of sense. So let's take, for example, I'm looking at problem number 39 from your textbook. So it's given as this. It says y prime plus y divided by t is equal to 1 divided by t y squared. It does give us an initial condition as well. We'll throw that in there for good measure. So to solve this one, I always like to first multiply by the y squared. So this turns into y squared y prime plus y cubed divided by t is equal to 1 divided by t. The reason I do that is it tells me whatever y's are going on in this term here is my v. So my clever substitution is let v equal y cubed. Then dv dt would be 3y squared dy dt, which looks a lot like that first term except for that 3. So I'm going to divide both, whoa, my goodness, divide both sides by that 3. That was much more extreme than I had anticipated with that eraser. Okay, let's minimize that a little bit. All right, great. So this then allows us to substitute into the yt equation here. So I'll again do it in white. So y squared dy dt, or in other words, y squared y prime, is now just 1/3 dv dt. Y cubed over t is now v over t. Or maybe I'll just write it as v times 1 over t. And the reason I would do that, as you'll see, is that it makes it a little bit more obviously linear. Great, now we solve this one. So now we've reduced it, but now the whole Bernoulli trick is done. So Bernoulli said, do this cool substitution. It turns these almost linear equations into linear equations. So to solve this one, dv dt plus 3 divided by t v is equal to 3 divided by t. So then we have a couple of options. If you want to do the homogeneous solution and then do a particular solution, we could do it that way. The reason I would say that is the particular solution is super obvious, right? V particular is just 1. Because if v is 1, then we get 3 over t. 0 plus 3 over t times 1 is equal to 3 over t. So there's a particular. So that would make it really easy if we find a homogeneous solution. So let's do that. So the homogeneous solution then would say, well, dv dt plus 3 over tv is equal to 0. So this, I'm going to subtract off this term, right? So I'm going to have dv dt equals negative, etc. So this is now separable. So if it's a separable equation, you can recall that we can write this as dv divided by v is equal to negative 3 over t dt. Integrate both sides, and you have natural log of v is equal to negative 3 natural log of t plus a constant. All right, great, good. Those absolute values, awesome. So now I'm going to take care of this negative 3 by putting it into the exponent of t. So we have a constant here. So now if I do e to the power of these, right, so I would have over here I'd have e to the power of the natural log to the negative 3 plus some constant, right? That's the same as the constant being in front of arbitrary constant, e to the natural log of this stuff. Well, wait a second, e to the natural log, that just gives us a constant times t to the negative 3. So this right here is helpful as a what do you call it? A homogeneous solution here. But what we don't have is y. Right? We actually want to find this y. So this is our v. So in order to find y, we're going to will this actually be homogeneous? First say, well, what is our whole solution of v? Our whole solution of v is v homogeneous plus v particular. So that would be k t to the negative 3 plus 1. And y cubed is equal to v. So let's just take a cube root. So y ultimately in yellow for gold, because it's a glorious golden moment. K times t to the negative 3 plus 1. And there you go. So another example of solving a Bernoulli equation by turning it into a linear equation.